probably pretty tired, I imagine, from studying for finals.
Oh yeah, it's pretty rough.
I'll bet.
Yeah.
I think I got it bad when I have 6 sessions in a row. It's
Huh,
not as
yeah.
bad as you guys have it with having to study for all those different subjects.
Yeah.
All right.
Alrighty. Well, so we are doing like a quiz in math that is going over like 2 sections, and it's over like evaluating trigonometric functions.
Okay.
Like for example, one of the ones I'm stuck on right now is 1 plus cosine of angle. I guess it would be over sine plus sine of angle over 1 plus cosine angle is equal to 2 cosecant angle.
And this is a verify?
Yes. Verify it algebraically.
Right. In other words, we're not solving for theta. We're verifying that the left is equal to the right.
Mm-hmm.
All right. When you're verifying trig functions and you run into 1 plus cosine theta or 1 plus sine theta, it is frequently a good idea to multiply top and bottom by the conjugate.
Oh, okay.
Okay?
Alrighty.
And the reason is that, let's just talk about why that works so good. The conjugate is 1 minus cosine of theta. Of course, if I multiply the top expression, I got to multiply the bottom by that also.
Yeah.
And the reason it works so good is because it converts the top to 1 minus cosine squared, which is then replaceable by a single term sine squared. Yeah. And look at how nice that's going to work on this problem. In other words, when I do this multiplication, I get 1 minus cosine squared in the top. And don't multiply the bottoms together. Leave them like this.
Oh, really? Okay, that was part of where I was getting hung up.
That's where everybody gets stuck. You don't want to ever multiply them because then you'd have to do more work to get it back into the form you need it in. In other words, since my next step is I'm going to replace that with sine squared, now I can cancel that sine of theta with that power, and this whole term has been converted to sine over 1 minus cosine theta. Okay?
Alrighty.
Yep. Now, it'll be easier. This side has 1 plus cosine theta. And I could do the same thing to this other side, but that's not actually going to be helpful. Let's go from this point here. What we have here is sine theta over 1 minus cosine theta plus this other term that looks similar. And let's do the same thing. No, let's not do the same thing. Let's add these 2 fractions. How would I add these 2 fractions?
Wouldn't you just multiply 1 by...
We would find a common denominator.
Yeah, but like I kind of don't understand how you would do that if the sign is in the middle. Like, how would you change that?
The common denominator is always the product of the 2 denominators.
Oh, okay.
So there's my common denominator.
Okay. Which you can FOIL out, right?
Well, yeah, and that becomes 1 minus cosine squared, which turns into sine squared.
Sine squared. Yeah.
So, but what goes up here in the top left? In other words, what?
It should be sine squared. Oh no, it should be 2 sine.
Well, it's sine theta times this 1 plus cosine theta. Let's go back as to how we let's go back as to how we do fractions.
Yeah.
The lowest common denominator is going to be this.
Right.
Well, for me to make this fraction have that denominator, I got to multiply it by 1 plus cosine theta over 1 plus cosine.
Oh, okay.
Okay, so I get sine theta times 1 plus cosine theta. So that's what that turns into. This one turns into sine theta times 1 minus cosine theta all over that same denominator, which now becomes 1 minus cosine squared theta. And the only reason I multiply that together is because I know I can replace it with a single term.
Yeah.
Okay, so this is 1 minus cosine squared theta. I'm going to replace both of these with sine theta, sine squared theta.
Okay.
Hold on, we'll get there.
Yeah.
Now, if you distribute the top and simplify it, you end up with sine theta times 2.
Okay.
So the top is sine theta, 2 sine thetas, all over sine squared theta. So I'm to this point right here.
So how did you simplify the top?
Well, I can factor out the sine theta, leaving behind this plus this.
Right. Oh,
And the ones add to 2, and the cosine thetas go to 0. So the top becomes sine theta times 2.
Okay.
Now I can cross out that in one of these powers. So I have 2 over sine theta, and guess what that's equal to? 2 cosecant theta, which is what we're trying to prove that it's equal to.
That is quite a long-winded problem.
It is. I'm sitting here thinking, did I do it the shortest possible way? And I might not have.
It's fine.
I think that there is a shorter way to do it, but you frequently run into that when you're doing these things.
Yeah.
In other words, sometimes you can find the 3-step method, sometimes it's a 7-step method, sometimes you do 8 steps and you have to turn around and go back to step 1 and start all over again because you're kind of lost in the woods. And
yeah.
so this is a bit of a strange one. I typically do this as my first step whenever I see this. But for this particular problem, it might have actually made sense to just go ahead and add the fractions in the first place. Your common denominator would be sine theta times 1 plus cosine theta and go from there. I think that'll get to the answer a little quicker if we do that. All right.
Okay. All right, well, just clear up my issues on that. The next sort of problem I've been having a little trouble with is factoring expressions.
Okay.
So the one example of the problem is cotangent squared x minus cotangent squared x.
I think you mean that.
No, it's minus cotangent squared x.
Okay.
And plus cosine squared x. Yeah, and the word factor kind of threw me because I didn't really know how to take anything. I don't know.
Okay. Think of this as x squared minus x squared plus 1. This was the problem, right? Or not? Parentheses around those last two terms?
It didn't have parentheses.
Did not have parentheses.
No.
Well, there's no real factoring to do. You just subtract that, cancels that, and you end up with cosine squared x.
Really?
Yeah, the only time this would be a factoring problem is if I had parentheses. Now I can take a cotangent squared x out, leaving behind 1. No, this problem doesn't make sense the way it was read. You sure it was cotan squared x
okay.
minus cotangent squared x plus cosine squared x?
Oh,
Because there's no factor.
no,
There's no
yeah,
real
it was
factor.
multiplication.
Yeah, there's no factor.
It was multiplication.
Ah.
Yeah, it was multiplication between the, yeah.
Okay, that makes more sense. Now I can factor out a cotan squared x.
Okay.
When I factor it out, what's left behind?
Just cosine squared x, right?
1. Remember when we factor something out, we have to divide every term by it. So I have to divide that by cotan squared x, leaving 1, and I have to divide this by cotan squared x, leaving
negative cosine. Okay, which becomes
sine squared.
Yeah.
And since cotan squared is cosine over sine squared, this whole thing becomes cosine squared.
Okay.
There's also, when you said that you have trouble with the factoring, let's go over this one right here, because this one you're going to have to be able to do.
Right.
You solve that. Solve that trig equation.
So, would it be sine x minus 2 and sine x plus 1?
Yes.
It would?
Yes. In other words, you factor it just like you would factor x squared minus x minus 2.
Minus 2, yeah.
This is called a quadratic in sine x. The other would have been called a quadratic in x. Okay, now we're not done yet. What's our solution now?
Would this be 2 and negative 1, right?
Well, you would have sine x equals 2, or
okay.
sine x equals negative 1. Now we still need a solution. In other words, our goal is to solve for x, not sine x.
Yes.
So first of all, can sine x be equal to 2?
Oh, no, it can't.
That's right. So that's an extraneous solution. That's impossible. The range on sine is -1 to 1. Now, so this leaves our only solution is that. Where in the unit circle does that happen? Where is sine x equal to -1?
Let me think about this for a minute. Okay. Quadrant 3? Or no, it'd be quadrant 4.
It's actually not one of the quadrants. It's on one of the quadrangles.
Oh, really?
Notice, what's this point? That's 2 pi.
Yeah.
That's pi. Here's where we're looking at right here. So it's that point right there, 3 pi over 2. So that's the only answer is x equals 3 pi over 2, or 270 degrees if you're in degrees. But probably when you're doing stuff like this, you're going to be in radians most of the time.
Okay.
Okay? So this actually becomes vital to memorize. You want to memorize the sine curve and the cosine curve. And the reason is that's the best way to answer the quadrangles.
Yeah.
What's the sine of 90 degrees?
I guess that would be quadrangle pi over 2.
Right. So what's the sine of pi over 2? From the chart. Just read it from the chart. Or from the graph. From this one down here. This is y equals sine x. This one is y equal cosine x.
Cosine x, okay.
In order to memorize the quadrangles, it's really helpful if you memorize these charts. You don't have to. There are other methods. But the thing is, you want to memorize these graphs anyway. You want to know all of the quarter points. In In other words, you know the function has a period of 2 pi, which makes the quarter points these right here. So what's the cosine of pi? Cosine.
180. Well, no.
No. Remember that when we take a trig function of an angle, we are always going to get a number or a ratio.
Okay.
We're not going to get an angle. You get angles when you take inverse cosines of angles or of numbers, you get an angle. But in this problem, I said, what was the cosine of pi? So go to the x-axis.
Right, so.
Find pi and look at where its value is.
I'm kind of confused. Are we talking about unit circle or the graphs?
We're talking about the graphs.
Well, I guess it would just be 0. Just be 0.
No, go to pi on the x-axis.
Right. Yeah.
You might be confusing the two graphs here. I switched back to the cosine curve here. So cosine of pi, I would go to pi, look down, that's my value, -1.
Okay.
So knowing these two graphs is going to allow you to answer all 4 quadrangles. The 4 quadrangles are 90 degrees, 180, 270, and 360.
Okay.
And those are hard to answer from the unit circle. I mean, they're not impossible. It depends on how you've been taught the unit circle, but those don't lie in any of the quadrants. In other words, it's a quadrangle because it lies right there between the first and second quadrant.
Yeah.
So it's hard to use the standard rules, and if you're basing all of your first quadrants on these 2 special triangles, well, they don't go to 90 or 0 degrees. So the way I've always suggested people memorize it is to memorize these 2 graphs, because you kind of need to do that anyway. Don't you? I mean, maybe you could get through trig without knowing these 2, but I don't think so. And if you have these 2 memorized, then you don't have to use the other technique that they teach you using the unit circle.
Okay.
Okay?
All right, so my other question that I had was on, this is a different assignment.
Okay.
I believe. Yeah. So it's, let me, I wrote the problem down differently. Okay, cosine x plus sine x times tangent x is equal to secant x.
Okay. They say that when you're trying to verify trig equations, if you get stuck, the last resort method is just convert everything to sines and cosines.
Yeah.
Go from there. Well, we already got a cosine and a sine, so it's not, and I know how to convert that to sines and cosines, and I know how to convert that to sines and cosines. So, what's tangent?
Sine over cosine.
Now let's add these. Now let's add these 2 fractions. How do I add these 2 fractions?
You mean the cosine x and the sine x?
Yeah.
Yeah. Well,
this not fractions. This with this fraction. How do I add those?
I don't really know.
Common denominator. What's the common denominator need to be?
Cosine.
Okay. So if I add that denominator over here, I got to multiply the top by cosine. So that's the same thing, right?
Yep.
Okay. Now I have a common denominator, and I can just operate on the numerators. So the left turns into this. What's sine squared plus cosine squared equal to?
1.
What's 1 over cosine x equal to?
Drawing a blank on this one. Oh, yeah. Sorry. Secant x.
Okay. It's it's okay to look at this because it tells you kind of the direction that you want to go to. They tend to frown on manipulating both sides. In other words, I don't know that I would want to right away say that that's 1 over cosine. That's probably not the way to go about doing these. Yeah. But as you're doing this, it's helpful to know what we're heading for, and we're probably going to, since we're turning everything into sines and cosines, we should end up with a 1 over cosine x on the left. Incidentally, they never give you an equation that is not an equation.
Yeah.
When they say verify this, that means that it is true. In fact, the cruelest thing they could do is give you a multiple choice verifying problem. That's much harder to do than a regular verifying by a factor of 10. The reason is that of your 5 multiple choice answers, 4 of them are wrong. So how do you know where to begin?
Yeah.
You begin with a wrong one, and now you're working on a problem that you've never done before. You've never had to try to verify 2 things that aren't actually equal to one another. And that's a whole other game. That's a different strategy altogether. So any teacher that does that really doesn't understand the thing. Yeah. You don't want to put multiple choice on trig verifying problems.
Okay.
We got about 5 minutes if you have a 5-minute problem.
Well, I think I do.
Fortunately, I have a 7:30 I'm going to have to go to, but.
Okay, so I think we'll do secant times negative x.
Okay, that's pronounced secant of negative x. It's not really times any more than you don't say f times x there. You say f of x. It is a function of x. And this is a trig function of minus x. So it would be secant of minus x. Okay. What else?
Over cosecant of minus x.
Okay.
Is equal to negative tangent of x.
You kind of have to know here odd and even properties of trig functions. Okay. Let's go over the primary ones. Sine and tangent are both odd.
Okay.
What that means is that sine of minus x is equal to minus sine x. Tangent of minus x is equal to minus tan x.
Okay.
Cosine is even.
All right.
Cosine of minus x is just equal to cosine of x. Like all even functions. So the first thing I want to do here, now if sine and tangent are odd, their reciprocals are also odd. And if cosine is even, its reciprocal is also even. So since secant is 1 over cosine, and cosine is an even function, I can write 1 over cosine x, or secant of minus x. Because secant of minus x is equal to secant of x, and secant of x is equal to 1 over cosine x. Cosecant x is the reciprocal of sine. So it's odd. So it's going to be 1 over sine x with a negative in front of it.
Okay.
How do we do this operation?
I don't.
Flip the bottom and multiply.
Oh,
That's
okay.
pretty much the way we do any kind of division problem where the bottom is a fraction. We don't
Okay.
even know how to divide that into that. But what we do know how to do is flip this over and multiply. So it becomes 1 over cosine x times a negative sine x over 1, which becomes sine x over cosine x, which is tangent x. With
And why wouldn't that be negative sine x over cosine x?
it is negative sine x,
Oh, sorry, I thought you said sine of x.
which is negative tangent x.
All right. Which is what the problem is equal to.
Right. That's what we're trying to make it be. And again, this problem had no sines, no cosines in it. But since everything could easily be turned into sines and cosines, that's what I did. In other words, we know how to turn this, this, and this into sines and cosines.
Yeah. All right. Well, pretty much takes care of all the questions that I had.
Okay. Sorry I couldn't give you more than a half an hour today, but this is a crazy day. Today and tomorrow are both crazy.
Yeah.
Is your final on Wednesday?
It is.
Okay. Well, if you like, if I get an opening, like a half-hour opening, I can call if you need more help tomorrow. But at this point, I am booked from 1:30 to 9.
Yeah. Okay, that'd be good. I probably won't have near as many questions as I won't have near as many questions as I did today.
Okay.
But
Do you feel like
you
feel like you still need some more help? If I do get an opening, do you want me to call you, or are you good to go?
Yeah, if you have an opening, you should probably call.
Okay.
Yeah, that'd probably be best.
I will, or I'll text you.
Okay, that works too.
Talk to you next time. Good luck if I don't talk to you again. Have a good Christmas if I don't talk to you again.
Thanks. You too.
Bye-bye.